character for this talk, which is a neutrino. And yeah, so we've been asked to sort of talk about the big questions in neutrinos. And so some of them have to do with neutrinos themselves and their roles in the universe. But we also think that sort of the detectors and experimental techniques are very exciting. And so we thought of this sort of generally in terms of what kind of things get us up every morning to do our work and what inspires us. And then, yeah, we'll close with a summary. So you want to go on to the next slide? Yes, Erica, maybe you can introduce yourself. We already. Yeah.
Okay. Yeah. So, and again, thanks for the great introduction, Christian. My name is Erica. I use she, hers as pronouns. So I did my PhD on double show studying neutrino directionality in a scintillator detector. And now in 2013, I moved up to Sudbury and started at Laurentian, and now I'm a research scientist there working on SNOW+, HALO, and NEXO.
Yeah, and so I'm Hirohisa Tanaka. I did my PhD on Babar, and since then I've been working on various neutrino experiments, usually accelerator-based, and I've been at SLAC in Stanford since 2018. So one thing we'd like to do during this this talk is to take a couple of polls. There won't be too many of these things, and hopefully some of you have had experience with this, but basically, we'd like you to maybe have a browser open to that, the website you see there, pollev.com, new questions 524. And we'll just try a few questions right now to see, to give the system a little warm up. So if you go to that website, maybe you should find that there's a map. And yeah, so the first question you'd like to ask is, where are you? And just to get a sense of where people are, right?
Show us the website again.
Sure, let me put it in. It's someone did put it into the chat window.
Oh, great, thank you.
Thanks, Patrick.
Oh, well, it's full and no longer accepting responses.
I've never seen that happen. Okay, hopefully that doesn't become an issue. I haven't seen that happen before. Okay, but it seems like most of us are sort of in the North American region. I saw a person appear and disappear from above the Arctic Circle, and then a couple of people in Europe. Excellent. So we had one additional poll question of a different kind, which is just, yeah, what do you think of, this? Yeah, so we move to a new question. Yes, so this is sort of a Wordle, so you can just sort of put in words there and let's just see what people think about.
I agree with whoever put in best.
Okay, great. So yeah, I think there's some, definitely, I'm sure people have heard about neutrinos, and yeah, we can sort of see the various interest in that particle, whether through what we think about them or experiments that do that sort of study them, or yeah, I guess there's some pseudo partisan things in there, but no, this is very interesting. So yeah, that being said, so I think everyone's kind of familiar with this. So let's well, we'll put the poll away for now, and then come back to the talk, and then we will have a poll question towards the end. Okay.
So then now moving on to talk about the neutrino and starting off with what we do know. Classically, it is a spin 1/2 fermion partnered with a charged lepton and a weak isospin doublet. So we can see how the neutrino interacts with the charged leptons via the W, and how it can react, scatter with other neutrinos via the Z boson. We often see the neutrinos down here as the neutral leptons in the standard model. We know that neutrinos have only left-handed weak interactions. They only interact via the weak force. They come in 3 flavors / anti-flavors, designated as alpha. So that's the electron, muon, and tau types. They have a small amount of non-degenerate masses, and that's generally designated as Mi. So we connect our left-handed neutrinos possibly with a right-handed neutrino. But this is, again, something that we still don't know yet. This is almost jumping the gun and getting into the questions. We know there's mixing between the mass and flavor states, and Hiro will talk more about that later. And we know that the flavor states are a sum of the mass states mediated through this, the mixing matrix. We know that neutrinos do not have electric charge, and they do not have color charge. And that's it. That's what we know about neutrinos. So I think Hiro wanted to add some things. Hiro's muted.
One of the things I find fascinating about the neutrino is that on the one hand, we have these properties, but so much of it is also determined by the properties that they don't have, right? And so, for example, the fact that if you have charge, then that's sort of, on the one hand, you bring yourself into all the wonderful worlds of electromagnetism, but then you also have this charge that you have to conserve. And so by sort of peeling away some of these properties, that's how we get the neutrino to have very unique, possibilities that we'll talk about.
Yeah, I agree. By having fewer of the properties that we're used to, we have more and more possibilities of what it could be. So then moving on to our first big question in neutrino physics, what is the neutrino mass? So we know that we have here the standard masses of the rest of the particles in the standard model, and they all kind of group together, and they're somewhat logical. And then many orders of magnitude down here, we have what could be the neutrino masses. So we don't know why they are so different, and this is certainly one of the big questions. I think they're all the big questions, but this is one of them. Why are neutrino masses so small? And so why are they not nothing? And then why are they so small? Non-neutrino masses. So Andre de Govia said very well. The non-zero neutrino masses imply new degrees of freedom. There's something that we don't understand yet. We don't know what they are, nor what are their masses. They might be light sterile fermions. They might be heavy sterile fermions. There might be a Higgs boson triplet. There could be all these methods of how neutrinos get their mass. That it could be this the standard seesaw mechanism that would imply a very large right-handed neutrino. We don't know what the nature of the neutrino mass is, so this is certainly one of the bigger up-and-coming questions. There are many different probes of how we can learn the neutrino mass. We can look at cosmology, and that the 2018 Planck results with some of the strictest parameters added in give us that the sum of the neutrino masses is less than 0.12 eV. And this also gives us the result that there are only three neutrinos. We can look at the direct evidence, Katrin and some of the other neutrino mass experiments, Holmes and Project 8, that these are the wonderful results from Katrin, and their neutrino 2020 results tell us that the mass of the electron neutrino is less than 0.9 eV. Neutrinoless double beta decay can give us hints into M beta beta, and there are a huge number of neutrinoless double beta beta decay experiments going on right now. So this is an image of Camland, but there are way too many to talk about in just one big questions presentation. But the long baseline experiments can give us hierarchy information. So this would be Dune, also T2K, and Hyper-K more. So here are some of the probes of neutrino mass, how we can search for what it is experimentally. So what we do know about neutrino mass so far comes from oscillation experiments. And those experiments tell us the differences between the mass states. And again, here we'll talk more about oscillations later. But what it has come down to is that we have two different orderings for the three mass states that we know of. We have the normal ordering where the third mass state is heavier than the first and second, or the inverted hierarchy ordering, where the third mass state is the lightest one. But again, we don't know how far away from zero either of these are, and we don't know which one is correct. And this is then an increasing order of mass. But we do know what these differences are from the oscillation experiments. And so these are the current PDG values. But again, without knowing the scale and without knowing which hierarchy is correct, there's just so many open questions. So one of the probes of the mass of the neutrino is then the nature is the neutrino, Dirac, or a Majorana particle. So if it's a Majorana particle, then the neutrino is its own antiparticle. And we can search for this using neutrinoless double beta decay. We can see if through two beta decays, if there is ever a time when we only see neutrinos as the end product. And this is possible for a handful of isotopes. Again, there are many, many experiments working on this. But looking at how often that happens, how often we see a signal, can give us then, depending on your phase space, which is different for different isotopes, and your mass, your matrix element, and those are large calculations, and there's many different ones, models for this. You can get a range of possible effective neutrino masses, which then also sum over the mass states. So this is from a presentation, again, from Neutrino 2020, where we have the results from Quarry and from Gerda and from Camland Zen. And this might still need a bit of updating, but we are just pushing into possibly seeing in the inverted hierarchy. But we will then also be pushing, hopefully in the next generations of experiments, pushing through to the normal, to exclude the inverted hierarchy and get into the normal hierarchy, if this is possible, and cosmology and the single beta decay experiments or the electron capture experiments that will give us just that the other mass measurements will push in from the right-hand side here. So hopefully in the next generation of experiments, this is one of the questions that we can answer.
Okay, yeah, so I'd like to talk a little bit about neutrino mixing and why I think we're in a particularly potentially interesting situation where I hope maybe in the future something very exciting will happen. So if you go to the next slide, we have this picture basically sort of describing the mixing that we have in the quark sector on the left and the neutrino sector on the right, or the lepton sector on the right. And so basically what we're looking at is how the mass and the flavor eigenstates relate to each other. And so I think when we first started getting information from neutrino oscillations about neutrino mixing, one of the really stunning things that people saw was that the mixing on the right, where you have these very large off-diagonal terms, is very different from what we have in the quark sector. We have a pseudo diagonal nature where there isn't very much mixing between these states. Now, which is normal and which one is strange is a bit of a historical bias. We measured the quark mixings to some extent first, and so that was sort of what we were used to. And then when we saw the neutrino side, it was quite different. But obviously, that's a bit of an arbitrary distinction. And so one point is that in the standard model, apart from a unitary relationship, there really isn't anything that the standard model tells us what these numbers should be. But I'd like to make the case that maybe that's something particularly interesting is happening in the lepton sector. But in either case, any explanation for why these numbers are what they are really requires a paradigm beyond what we have now in the standard model. And so if there's an explanation, that is really new physics that has been staring at us some time, and would provide an explanation for these otherwise seemingly random numbers that we observe. If we go to the next slide. So in terms of the neutrino sector, I think one of the things that's very interesting is some of the values which may be emerging. So maybe one thing that's better established is what we call the parameter theta 2,3 or the mixing in the heavier neutrinos. And so what you see on the top here is basically what happens to muon neutrinos as they go from production to some distance, in this case, about 800 kilometers away in a nova detector. And so what you can see here is that basically the muon neutrinos almost fully convert into some other flavor. And that's indicative of what we call maximal mixing, the idea that somehow there is that basically that this transition can happen almost entirely, if not completely entirely. And so that's a very interesting and suggestive thing that has been begging for an explanation for some time. And there have been hypotheses about whether there are underlying symmetries that govern this. On the bottom right, you sort of see some of you see similar data from the TDK experiment where we're looking at either muon neutrinos or muon antineutrinos turning into their electron counterparts. And what that experiment sees is in fact sort of a maximal effect where the oscillation probabilities are maximally different between the neutrino and the antineutrino sector, and that leading to what this phase that drives the neutrino, the CP violation to be something like 3 pi over 2 or minus pi over 2, depending on which experiment you're in. Now, NOVA doesn't quite see that effect, and so you can sort of see that in the plot on the upper right that there's an interesting situation, which is not uncommon, that there's definitely some degree of tension between these two experiments. But nonetheless, yeah, the idea that these numbers are coming out to kind of interesting values a priori, I think is a very interesting possibility. So if we go to the next slide, I think, yeah, people have been thinking about this for some time, and in particular, there are these flavor symmetries that can sort of give you a sort of an approximate starting point for these observed mixing. And so one thing that's been talked about for some time is the idea that maybe the underlying pattern is this tri-bimaximal mixing that you see illustrated in the matrix B there. And so these models actually do give predictions about what these numbers should be, and so that motivates precise measurements that will be done by future experiments. So one historic analogy I like to think about, and this analogy can break down at any point, is that sometime 150 years ago, people started studying the emission from atoms, in particular hydrogen, and so people like Balmer and Rydberg discovered a pattern in the hydrogen emission pattern, which you might recall is sort of this Rydberg with the differences of 1 over n squared, where n is an integer. And that was a starting point where the eventual explanation of that required the development of quantum mechanics and a full understanding of how an electron binds to a proton, and required it was really one of the largest paradigm shifts in scientific histories. So for neutrinos, we're still at maybe step 0 here. We're still trying to see whether there's a pattern and where we go from there. But to me, if there is an explanation for this, then it's something that's really terribly exciting and something that certainly motivates me to pursue these precision measurements. So maybe we can go to the next slide. I think we changed topics here, so I'll turn it back to Erica.
Yes, so part of answering these big questions is how do we, we're both experimentalists, how do we build a machine to help us answer them? So again, kind of stepping back a bit, I find fascinating the history of neutrino detection, starting with Reines and Cowan, who were both at Los Alamos working at the bomb and the lab there and doing development there. So they had thought, maybe we can detect neutrinos, these particles that probably have oscillated, but we don't know what they are yet, or if they actually exist. If we set off a nuclear bomb, then we can see the positron or the neutrino hitting a proton, or an antineutrino actually, hitting a proton and creating a positron, and these two gamma rays that come off, and they can ionize and create light in our liquid scintillator. And we can have this detector hanging, just suspended in a deep hole underground, and we can time setting off a nuclear bomb and cutting the cord and dropping the detector so that it won't break from being shaken because of the explosion of a nuclear bomb and fall through a vacuum onto feathers and foam rubber. And this was approved. This was an approved plan for the experiment. That, I mean, things were different, different many, 50, 80 years ago. Life was much simpler in these days, Rhinus said. No lengthy proposals or complex review committees. So I think I'm glad that we've moved on from this stage, and that they had realized that instead of just capturing the signal from the positron, you can also capture the signal from the neutron. So they ended up building in Savannah River these tanks of water as a target, and then a scintillator to see the gamma rays. And they dissolved cadmium chloride in the water for the neutron capture. So when they realized that they could see the neutron as well, they thought, we don't need a bomb. We can go next to these, again, new-ish at the time, nuclear reactors. And then we can have a constant source and we can repeat this experiment. So I think this worked out for everyone. So they came and they had their results and they were looking promising. But as we do as experimentalists, they wanted to double check all of their results. So they dissolved some cobalt in the water to understand the positron signal, doubled the amount of neutron targets in the water to watch the time decrease for the neutron capture, put heavy water in the tank instead of just light water, which would make the inverse beta decay cross-section decrease, and then vary the shielding to make sure that the signal is actually coming from the nuclear reactor and not from cosmic rays. So I think we all know that the end point of this is the success. So I enjoy much these images of the telegrams that Rhinus and Cowan sent to Pauli saying that we definitely detected your neutrino, and Pauli writing back saying everything comes to him who knows to wait. So I think that's a message that we can take away from this is we've been waiting a long time to answer some of these questions, and maybe it will take some more time. But then getting back into the detector technology, one of the stalwarts of neutrino physics has been the water shrink-off detector. So you have a particle, a charged particle traveling faster than the speed of light, and it creates this shrink-off ring that can be, depending on how you look, will always be a ring in your detector. So we have SNOW, and then the first phase of SNOW Plus was also a water shrink-off detector, and of course Super K, and this is an event display from Super K. But more recently, in the past 10, 15 years, we have these more volumetric water shrink-off detectors that instead of instrumenting the outside, the surface of these detectors, they are using the entire ice or the Mediterranean Sea or Lake Baikal or the Cascadia Basin to be their detector, or to be their the detector medium, and filling in with often multi-PMT optical modules. And then so you get a very different kind of event display and a different analysis for these kind of water shrink-off detectors. So we also wanted to recognize here Masatoshi Koshiba, who passed away just last week. And if I believe the slides will be made available, but there's a very interesting article of how he and his team worked with Hamamatsu to develop the giant 20-inch PMTs that are in Super K, and an amazing video of them actually blowing. All the PMTs were hand blown. So those are links there, but this is an image of him in the initial construction phases of Kamiokande. So moving on to another technology, liquid scintillator. So one can go lower in energy with liquid scintillator than you can with a water strength-off detector or ice strength-off, because you have a lower threshold for the neutrino interaction. So NOVA uses solid scintillator strips in alternating patterns to instrument their detector. Borexino uses just pure liquid scintillator and double show, and many other experiments use dope liquid scintillator. So double show, Reno, and Diabay put gadolinium in their liquid scintillator to increase the neutron capture. Prospect puts in lithium, which also has a high neutron capture cross-section. So for looking at inverse beta decay, making sure you capture your neutron is very important. So this is one technique. But Coherent also uses a cesium iodide scintillator doped with sodium for coherent neutrino scattering. So again, just one technology of which there are many different ways to go. Another doping of scintillator is with a double beta decay isotope, which is what Snow Plus and Camel and Zen do. And now we move to time projection chambers. So you have a volume that is often next oriented with a neutrino beam, and as a charged particle will come in, then you ionize, you drift the electrons to the collection plane, and because there's an electric field here, and this is an event from the microboon detector. So this is actually, again, relatively old. The concept is relatively old technology for something that's now being utilized much more. So from the original design paper that Carlo Rubbia had from CERN, that it appears possible to realize this liquid argon time projection chamber. Preliminary investigations seem to indicate this would be feasible with simple techniques. And I don't think anyone who works on a TPC thinks that they're simple. I don't think any of these detectors are simple, but it's interesting how so many of these ideas have come and then were created and then have been developed more over time. So other liquid TPCs are, again, with noble liquids, are Protodune, so the prototype for the Dune detector. This is at CERN right now. And EXO 200 was filled with liquid xenon. And so Nexa will be as well. So these are just, again, different uses of liquid noble TPCs, and they're very common in dark matter experiments as well. So finally, one last detector technology to talk about here are growing crystals. So this is, again, often used in dark matter experiments as well, but you can grow your crystals out of different elements, and often these are ones that are used for neutrinoless double beta decay experiments, both experiments here. Quarry uses tellurium, and Garrett uses germanium. And there are Legend also, Candles uses calcium and for double beta decay experiments. So this is one more technology, and I'm sure there are others that we haven't mentioned, but we were supposed to be a bias talk, so I think that's okay. Hira?
Yeah, I just wanted to say a couple of things, just reflecting on these neutrino detectors. So when I started started in neutrino physics, I worked on Miniboon, which was a mineral oil Shrank-off experiment. And I was sitting in a talk that's kind of like this one, looking at the future of neutrino physics. And a prominent member of the collider community commented or asked, yeah, will the next generation of neutrino experiments use the same miserable technologies that you've been using in the past? And yeah, I had to say I suffered a bit of an inferiority complex following that, looking at people, I guess people working on Atlas or CDF with their silicon detectors or crystal calorimetry and so on and so forth. But to me, there's something really almost poetic and beautiful about the fact that we can probe neutrino properties with something as commonplace as water, and that it basically have all the essential properties to answer some of the biggest questions about in science through these detectors. And obviously, there's also things like using geological features like the South Pole in the ice there, or the ocean, or a mountain. And so the way I see it is that to answer some of these big questions, we're going to need more very clever ideas like this. And so I hope that that people on this call will eventually come up with those ideas and allow us to move forward on some of the questions that we're talking about. Yeah, so let me talk a little bit about now looking up into the sky and what is the role of the neutrinos in shaping the universe. So going to the next slide, the neutrinos are the second most abundant particle in the universe after photons. And so it's in some sense not surprising that even in the very brief moment after the Big Bang where they were actually interacting with other particles, that they leave a profound impact. They definitely leave their mark in the formation of the universe, whether it's through the large scale structure or features of the cosmic microwave background. And so even their minuscule masses are something that we hope to see through the cosmic microwave background or through large scale structure. And so there are several really big questions that are embedded here. First is that, well, I think one nice thing is that we definitely see the impact of neutrinos on the CMB. And so that, for example, allows us to measure what we call the number of light relativistic species and effective. And so that number is kind of like around 3 as we might expect. We haven't quite reached the sensitivity yet with these experiments to see the neutrino mass, but with CMBS4, it's possible that or quite likely that we will see it, and that'll be very exciting. And so those are definitely big questions that are out there. And for me, another really exciting thing, or really something that maybe blows my mind a little bit, is the question of whether we will actually see the neutrino counterpart to the cosmic microwave backgrounds. And so while the photons we definitely see them, the neutrinos are out there, and we see their impact indirectly. But yeah, can we detect them directly, and what will they tell us? I think is just a question that to some extent blows my mind. And so people have some ideas, and it will be interesting to see where they go. So if we go to the next question, next slide rather. There's also the question of the baryon asymmetry of the universe, and a fancy way to say, why is there matter everywhere we look? And well, in some sense, what's interesting is that it's not just that there's matter everywhere we look, but in fact, the imbalance that creates all the matter that we see today is a very tiny one. In some sense, it is only a part in 10 billion in which the matter that exists now survived from all the annihilation and basically erasure of matter and antimatter through these annihilations that occurred in the early universe. And so that little smidgen that's left over, a part in 10 billion, basically is all the matter in the universe. And in some ways, one can ask this question in terms of why the universe exists at all, because if that imbalance didn't exist, then everything would have annihilated. And so it's been clear that to explain this, we need new sources of matter-antimatter asymmetry, or imbalances, which we call CP violation, beyond what we have seen in the quark sector. And so there's sort of two questions that are embedded here. So first of all, do neutrinos exhibit CP violation? And so going back to some earlier slides, we saw, at least according to T decay, there's maybe some indications that we're starting to see something. Nova would disagree with that, but so that definitely remains an outstanding question that will be addressed by, will continue to be addressed by T decay Nova, but may require future experiments like Dune and Hyper-K to definitively answer. And so that answers a very important question as to whether there is CP violation in the neutrino sector. But then there's yet an even bigger question, which I think we are still struggling to answer, which is whether that CP violation has anything to do with this baryon asymmetry in the universe. And that requires some theoretical work. And it really, it's not clear what the answer is and whether we will ever have an answer. But if really a connection can be made between the CP violation we possibly observe it in neutrinos, or whether that is actually responsible for why we exist, that would, I think, would be one of just a tremendous achievement for our species. So maybe going on to the next slide, I'll talk a little bit about additional properties that neutrinos could be hiding. Going on to the next slide, I didn't want to say too much about this because this is huge, right? I don't think we can even fit this into one talk in a comprehensive way. But some of the things I like to think about is, people, you're familiar with the standard model. Somehow fermions come in 3 generations, and there's not particularly good explanation for that. And so a question that people have asked is, could there be additional types of neutrinos or additional species of neutrinos beyond the 3 that we know of? And we know that somehow neutrinos may be different from the other fermions in the standard model. And so why should they be bound by this rule of 3 families or 3 generations? And I won't go into the details, but for reasons based on previous experiments, we know that if those species exist, they will have to use an even more exotic form of particles which don't participate in the weak interaction. And so that's why you often hear about sterile neutrinos. So a big question is, do such particles exist? I think as we start to think more about what the nature of dark matter is, there's been just an explosion of ideas about how maybe new sectors of particles and interactions may be responsible for that dark matter, and whether the possibility that the neutrino among other particles may have some mixing or what we call a portal interaction with that dark sector. And so this is, as I said at the beginning, such a broad question that I'll just leave it at there. And it'll be interesting to see what happens over the next several years or decade as we continue to probe these questions in the short baseline program at Fermilab and elsewhere, more generally within the dark matter efforts. So I think I turn it back to you now, Erica.
Yeah, so moving on. This is maybe a glib way of saying it, but are neutrinos good for anything? We're trying to study them and what are their properties and using them to understand the universe, but can we use them to understand anything else? Is a question I find really interesting. So of course, we first think of the supernova 1987A. And so this was, again, a telegram sent to Jean Beyer from a colleague, Sid Bloodman at Penn. Sensational news, the supernova went off. So Jean was at Kamiokande at the time. Says, can you see it? This is what we've been waiting 350 years for. Like, this is, what can we do with these neutrinos? So it turns out that Kamiokande did see a number of events, and so did IMB and Boxton. And together, these 25 neutrinos, 25 events have really started the age of multi-messenger astrophysics. And what can we learn from these neutrinos? So here is a plot of showing what the different neutrino fluxes are for electron neutrinos and antineutrinos, and then muon and taus together, plus the other signals from just one model of a supernova explosion. And we also see here these pre-supernova electron antineutrinos. So there are many different supernova models that we can hopefully start to constrain when we see another supernova and detect the neutrinos from that. So the SNOOS collaboration, which I forgot to mention I'm also a part of, is tying together the data acquisition systems and certain triggers of a number of experiments from all over the globe that are sensitive to supernova neutrinos in all different reactions and all different kinds of detector technologies. So to hopefully let us use these neutrinos to learn more about the supernova process. Can neutrinos be useful for the sun? I mean, Borexino has shown us how the sun burns through every neutrino interaction. So here is the solar process. So we get neutrinos from the proton-proton fusion, from the PEP signal, from the boron 8 and the beryllium 7, and then just recently at Neutrino 2020, Borexino was able to measure the CNO neutrino cycle from the sun. And so I think learning how the sun burns, one of the first big questions that we had in neutrino physics starting in the 1960s. It's now we're starting to finally nail down all of the answers on this, and neutrinos have told us this. One of the things that I think is a really interesting use of neutrinos as their own tool is nuclear reactor monitoring. So this is from the SONGS experiment that was next to the San Onofre reactor. And the data points are the counts of neutrinos, detected antineutrinos per day. And they could match that to their predicted rate depending on fuel consumption. And they could see when the reactor turned off and then turned back on again. So if we can measure the output of nuclear reactors, if we can, and from a distance, this happened to be very close, but the Watchman experiment at the Advanced Instrumentation Testbed in Volby Lab is looking if you can do this from farther away. This is 25 kilometers away from their reactor cores. So this is a large water shrink-off detector that will be doped with gadolinium. So again, we can dope not just scintillators, but we can dope water too with different isotopes to monitor nuclear reactors for understanding them for safety and for maybe better, safer monitoring as well. And then, of course, getting back into multi-messenger astronomy, this is, I'm totally forgot to put this on here. This is the Blazar TXS 0506 056 that IceCube saw a burst of neutrinos from on September 22nd, 2017. And so they put out their alert saying, hey, we saw something. And then other telescopes looked, and they also saw a signal from this blazar in the high energy and very high energy gamma rays, in X-rays, in the optical band, and in the radio wave band. So using all of these different instruments together to learn more about this one blazar. And then what other astrophysical phenomena can we do this with now that we have realized that this is possible? And IceCube then looked back in their data. Where else have we seen large amounts of neutrinos coming from this direction? I think this is such an interesting use of neutrinos to tie into particle astrophysics. And now, I mean, maybe this is getting a little bit more ridiculous, but can neutrinos send messages themselves? So at Fermilab, the accelerator that the booster, I don't think it's booster beam, that Minerva was using, they encoded a message into the structure of the burst of the protons as they decayed through, and that Minerva was then able to reconstruct the message that was encoded in this burst. And with an overall data rate of 0.1 hertz, but there was a less than 1% error rate, they were able to reconstruct the message. And of course, the message was neutrino, but that wasn't known a priori. And this illustrates the feasibility, but also perhaps the significant improvements in neutrino beams and detectors required for practical applications. I don't know if anyone thinks we're going to have tiny accelerators and all tiny detectors and know exactly how to point them to send messages. But if right now we're bouncing cell phone signals and this broadcast is being bounced through satellites across, in the sky, when maybe we could be sending it through the Earth instead, the fact that we're starting to look at these things, that we're starting to develop the technology to be used for, I think this is, again, part of what gets us up in the morning. What else can we do with the things that we're learning? So I'm going to finish off this section with another quote from Fred Reines. I don't say that the neutrino is going to be a practical thing, but it has been a time-honored pattern that science leads and then technology comes along, and then put together these things make an enormous difference in how we live. Electricity was a parlor trick. Maybe we could tax it. And now runs our life. So I think seeing how we can use the neutrino as we are learning about it itself is certainly something that we need to be thinking about for the next generations.
Okay, yeah, so I think we're coming to a close. I think one of the things that we wanted to mention was just how broad the field of neutrinos is. And I think many of us are attracted to, say, particle physics and cosmology because there is sort of this loop that connects the our understanding of fundamental particles to basically why the universe is the way it is. And that's certainly true for neutrinos, as I hope you have seen that, something like the nature of neutrino mass may connect us to very high physics happening at very high energies, far beyond what we can currently probe with colliders. But then, once we start understanding the properties of those neutrinos, then they start to serve as probes with which we can understand things like the structure of the proton or a nucleus. Then we can start using them as sort of even probing things like the Earth or understanding the dynamics of a star. But then eventually they become messengers, as Erica was discussing, where neutrinos from far away, from some galaxy far away, tells us something about exciting things which are happening over there. And then going to larger scales, how we come back to how the neutrino properties themselves drive how the universe has evolved to its current state, including possibly why it exists at all. And so, yeah, for people looking for opportunities, the neutrinos offer just such a wide palette of questions, experimental techniques, length scales, energy scales with which to do very exciting and fundamental work, which I hope you've seen through these big questions. So maybe if we go to the last slide. So yeah, that was our biased view of some of the big questions in neutrinos and some of the things that we find interesting or exciting. So we do have one last poll question for you, which is basically we had several of these questions, and we'd like to see, what you thought was most exciting. Oh no!
Like how,
I hope people got a chance. I've never seen that before, so I don't even know how you would test to see when you hit the limit. But it's interesting. Yeah, there's quite a spread of interest, and yeah, the connection to shaping the universe is one that's I think both an exciting one where we have immediate prospects where exciting things will happen in the next few years, in a decade, and then at the same time, there's room both for major theoretical development, experimental development to really sort of nail down some of the bigger questions that we don't know quite how to answer. So so Eric, I think that brings us to the end of our talk, and so I think we can open up for discussions, and then and then here are our emails, and because I think both of us would be happy to continue the conversation beyond the talk we have here today.
Really, really great. Thank you so much. That was a really wonderful tour through the world of neutrinos. So yeah, I would encourage people to click the raise hand button, and we can call on you and go through questions. So maybe I'll start with one while people are thinking theirs over. So I'm curious. So I clicked the answer to, is there an underlying theory or pattern to neutrino mixing? So I'm curious, for some of the models that you mentioned where you add a discrete symmetry or have some discrete symmetry explaining this, are there other testable predictions that these models make? For example, like for other parameters that you could measure? Would they have anything to do with delta CP or targets for Majorana masses, or whether other measurable parameters take values you could uncover?
So the good news is yes, you can choose some kind of symmetry model and it will give you predictions. One of the things that Sergey Petkov, who gave a very nice talk within one of these SNOMAS frontier meetings, is that in terms of delta CP, Because the flavor symmetry somehow is agnostic between neutrinos and antineutrinos, it gives predictions for cosine delta, but not sine delta. And so that's yes. And so in general, yeah, they do predict neutrino mixing values, including delta CP. Maybe the bad news is that, you know, any number of symmetries that you can choose, and basically you can get many different answers depending on which one you choose. And so that's where precision may help us to eliminate some of these potential models. I think one thing I didn't talk about is that there are also, I haven't heard about this too recently, but there are also these sort of quark-lepton complementarity models where somehow the mixing you see in quarks is related to the mixing you see in leptons. And I don't know whether that's sort of fallen out of fashion, but that's sort of another class of models where, yeah, there are interesting relationships that otherwise would be arbitrary within the context of the standard model.
Thanks a lot. So Josh, do you have a question?
Sure, thank you. And I may be asking this of the wrong couple of people, but if you have anything, I'd appreciate it. As far as the reason why there are, I think, 3 different lepton families and quark families, as I understand it, is due to anomaly cancellation of the chiral anomaly, where you have to have 3 in the standard model. You have this miraculous thing where if you have 3 leptons for 3 lepton currents to every baryonic current, you basically have anomaly cancellation. Is there an understanding of if there are extra degrees of freedom, 4th, 5th, 6th neutrinos, how that particular cancellation occurs, and if it does at all, or if there's a sign that if we do see something like a sterile neutrino, that we still need even more physics beyond that?
So I think so the question, if I understand it, is that what are the implications for this anomaly cancellation if there are additional species of neutrinos, let's say sterile?
Yes.
I'm not sure if I'm qualified to answer that question, but I'm trying to see what I want to venture a guess. Maybe I'll throw it to Erica. Do you have any thoughts on that, or?
No, that is not in my area of expertise.
Maybe you can throw it to the audience as well if someone feels they can definitively answer that question.
Yeah.
I mean, I would just add that it depends a lot on what the new states are charged under,
Exactly.
right? So it's a model-dependent question. If you did find a sterile neutrino, you'd like to know more about what it talks to. Is it simply a singlet, or is it charged with the new symmetry groups, for example, or does it carry baryon number, for instance? That's an intriguing possibility. So that would have consequences for the anomaly cancellation, but I don't think it's a guarantee that you learn something about anomaly cancellation if you found a neutrino, another neutrino.
Thank you.
Thanks.
There's a question in the chat about sources of CP violation. So you said that for the source of CP violation is needed, how much of the observed baryon asymmetry in the universe can be explained by the known channels of CP violation? That's a good question.
Yeah, so there is an interesting paper from a while back about, you know, whether it's possible that the light neutrinos themselves and the CP violation within there can be responsible for this asymmetry. And so the key sort of parameter there is this, you know, basically the Yalls-Cog invariant, which is some combination of the mixing angle and the CP phase. And if there's sort of a lower bound on that, which if it's bigger than that, then it can, you know, potentially give rise to enough CP violation or asymmetry to explain the baryon asymmetry in the universe. Now, as far as the other source of CP violation we know about, which is in the quark sector, I think that's short by many orders of magnitude to our best understanding. I know there are people on this. I'm just looking at the list. There are other people here, like I think Sergey is connected, who probably have you know, who can give a better, answer to that as well.
Okay. No, you answered it quite well. I mean, the only thing I can add is that if you assume hierarchical neutrinos, heavy Majorana neutrinos, and then you use you consider the simplest possibility having two heavy Majorana neutrinos, then this lower limit reads as follows: the absolute value of sine theta 1 3 times sine delta should be bigger than 0.1. And now, given the fact that sine theta 1 3 is 0.15, I mean, and if sine delta, if delta is around 3 pi over 2, you are there. So with the indications we have, I mean, this lower bound is comfortably compatible with the indications we have about delta. Of course, the situation with delta now is very confusing and not very clear in view of the latest T2K and NOVA data, but hopefully that will become more clear, say, within a year or 2 years. And if indeed delta is around 3 pi over 2, it would be great, really.
Yeah, exciting. Okay, I know. Matthias had a question.
Yeah. So I saw someone mention the detector technology in neutrino physics being kind of the same for several years, but I was wondering, how about the beams? How much do we expect the neutrino beams to change over time? Because currently we have the same kind of recipe of shooting protons at targets and right, like accelerator neutrino beams. Do we expect them to change much in the future? What's the plan here?
Yeah, so I think personally, I think one of the big questions for SNOMAS is, there are options on the tables. For example, muon-based neutrino beam, where you have some very nice features. You would probably have a very good understanding of the neutrinos you're producing, because you're basically dealing with a leptonic system. You have basically 4 flavors that you can produce. You can count anti-flavors. And this idea of a muon-based neutrino beam has been around for a while. And I think one of the big questions for SNOMAS is this time coming? is this a time where we say this is something we need? Probably not next year, or not. It's not going to be next year. It's not going to be. It'll probably take a while. But I think the purpose of SNOMAS is to look on sort of decades time scale and see whether this is something that will help us answer some of these big questions. And I don't know the answer yet. And I'm so hoping that through this process of community discussion, we'll come to some kind of consensus.
Mm-hmm. Yeah, I guess it depends what the post-Dune and Hyper-K era looks like.
Yeah.
Thank you.
Okay, I think there's a question from Matt.
Yeah, hi. Thank you for the nice talk. It was super fun. I had a question. It's maybe a little silly, but I really liked the part that you mentioned, Erica, about sending messages using neutrinos. I hadn't heard about that before, actually. And I'm just curious, I haven't looked at the paper yet, but why? Did the authors speculate on like any reason that we might want to do that? Or like, I mean, it's a cool proof of principle, but it seems very sci-fi to me.
Yes. I don't disagree that it seems very sci-fi. So in doing some more research for this talk, and I don't remember when now, but it had been mentioned, maybe it was also by Rhinus, of this is a thing that we could possibly do, is you use neutrinos for this. So I think when you have a detector that's built to capture neutrinos in such a way that Minerva was, so Minerva was a cross-section experiment that had different targets in front of its main detector to study and put measurements on the neutrino cross-section for capturing on different elements, which is very important for many experiments now. It's a really important experiment. But I think maybe the possibility of, hey, we could do this. Hey, this won't take too much time out of our initial physics goals. I think that's a great reason to do something, is because you can, because you're probably the only experiment at the time that could make this measurement. It is 100% sci-fi. This was getting into the point of what are the crazy things we could do with neutrinos. There were a number of crazy ideas that we had kind of looked at but didn't decide to extrapolate on. Could you use a neutrino beam to disable a nuclear bomb? Could neutrinos be why certain proteins have a certain chirality? Could neutrinos be used to see how quickly, or to see how susceptible an earthquake is? It was a neutrino earthquake tomography was another article I found. So there are really, really different kind of esoteric ideas of things that we can do with neutrinos, that we decided we wanted to kind of limit it here. But also, why not think about these things? This is what we're trained to do, is think of these really interesting ideas. Like, all science was at one time fanciful. Every idea we've had was like just this insane idea that we have refined and understood and made simulations about and made prototype detectors and have turned things into the actual scientific results that we see. All of the knowledge we have now, the awards that people have gotten, but the development is really the knowledge, and how much more we know has all come from what was once these crazy ideas. So who knows?
Right.
But
Now,
that's
all those crazy ideas, only one of them has to work in order to change the world.
Yep.
Cool. Thank you.
Thank you.
I think that's a really great and really inspiring place to maybe end the chat today. So yeah, I wanted to thank you both again for giving this really, really nice colloquium. And yeah, thank you everyone for attending. And we will see much more of you throughout the SNOMES process that'll continue for the next month. And I like to, encourage everyone to participate and think about how we can go from, ideas to future facilities and measurements, maybe 40 years from now, but we got to start thinking now. So thanks everyone.
Yeah, Christian, Matt, and Cindy, I'd like to really thank you for organizing this series. It's really very nice and a great service to to the community. I think it's very important.
Yeah, I really like the format of having two speakers and two who don't necessarily work on the same things, to give these alternate perspectives, and this has been great. Thank you.
Well, it's definitely a harder thing to give than the usual. So you guys were really good sports. So I really appreciate it.
It was a pleasure.
All right, and again, if anyone has any continuing questions, our information is in the slides.
Excellent. Okay, thanks.
Thank you.